name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to Talk 2 in the ITS RF Measurement Seminar Series. This talk is Fundamentals of Spectrum Analyzer Design. In the first talk we discussed thermal noise, KTB. In this talk we'll discuss how spectrum analyzers are designed. We'll look at both analog and digital designs. We'll see that both designs are fundamentally the same. A spectrum analyzer, as the name implies, is designed to show us power in a spectrum as a function of frequency. As we'll also see, it's possible to run a spectrum analyzer in a 0 Hz span mode in which we actually see power as a function of time. But the important thing to remember is that the spectrum analyzer normally shows the actual power in a measurement circuit, not the voltage. With that said, every spectrum analyzer starts with an RF input that we'll draw this way, RF. And then, at the RF input, we have a variable RF attenuator that we'll draw like this. The RF attenuator is usually adjustable for values that can run anywhere from 0 dB of input attenuation to 70 dB of RF input attenuation. And I'll write the functionality with a separate color. This input RF attenuator controls dynamic range for the measurement system. If we have a weak signal that we're trying to measure, we can go to 0 dB of RF attenuation. If we have a strong signal that we're trying to measure, we can go up to 70 dB of RF attenuation to avoid saturation of the spectrum analyzer front end. By the way, people often worry about burning out a spectrum analyzer front end. It's actually not terribly easy to do unless you're working with a very high power transmitter. The usual limit is plus 30 decibels relative to a milliwatt. That is to say 1 watt of input power average as a safety limit before the spectrum analyzer front end would actually burn out. Below that power level, you may saturate the front end, but you probably won't actually damage the spectrum analyzer. Now, following the variable RF attenuator, we have a choice which is generally operator selectable. We can either run through a low-pass filter, which I'll draw like this, and this low-pass filter is generally functional over the frequency range of 0 to 3 gigahertz for most spectrum analyzer designs. Or, if we're working at higher frequencies, we can run through a tunable bandpass filter, which we'll draw like this with an arrow to show that it's tunable, which is generally based on yttrium iron garnet, YIG technology. YIG technology, by the way, allows us to build microwave filters because the solid state material in the filter responds with a passband which is a function of a voltage that is applied to it. So this filter has a voltage applied to it which is proportional to the tuned frequency of the spectrum analyzer, and that automatically tunes this bandpass filter. And we have a switch at this point, and a switch here, like so. A lot of spectrum analyzer designs will actually switch this automatically depending upon which frequency you're tuned to. And where the low pass goes 0 to 3 gigahertz, this filter will typically go from 3 to 18 gigahertz or 3 to 26 gigahertz, depending upon your spectrum analyzer design. Now, this functionality is designed to prevent overload by the spectrum analyzer on strong signals that are not on the frequency that you're measuring. So this is overload isolation from strong off-tuned frequency signals. And by off-tuned frequency signals, I mean signals that are not on the frequency that you're trying to measure. Note something. This low-pass filter is in fact wide open from 0 to 3 gigahertz. It is in fact a fixed bandpass. So if you're trying to make measurements on a signal at, let's say, 2.5 gigahertz, and you have a very strong signal coming in from a broadcast transmitter at, let's say, 170 megahertz, that 170 megahertz transmit signal can overload your front end. Many spectrum analyzers are specified as having Yig tunable filters at the front end, but what they often don't tell you in the sales literature is that that filter only works if you're tuned to frequencies above 3 gigahertz. So be aware that you can overload the spectrum analyzer with strong signals below 3 gigahertz while you're measuring other signals on different frequencies below 3 gigahertz, and that this front end filter, which is a low pass filter that cuts off at basically 3 gigahertz, will not prevent that problem if both the signal you're measuring and the strong overload signal fall below 3 gigahertz. Now, the next step in our system is to either pass through a low noise amplifier, which I'm going to draw like this, or not. And we'll draw the straight through path without the LNA like this. And again, the selection is controlled by a relay switch. The point here with the low noise amplifier is to allow us to overdrive the noise figure of the spectrum analyzer downstream from this point by using low noise preamplification. We'll see why we need to do that in a moment. If you're looking at relatively weak signals, you'll want to select the low noise preamplifier. If you're looking at relatively strong signals, you won't need the low noise preamplifier and you can go to the straight through path. In some cases, in fact, a signal is so strong that it would actually overload the LNA, in which case you need to go to the straight through path. So we'll label this straight through path. And this is operator selectable, normally, with spectrum analyzer designs. One other thing to be aware of, in most spectrum analyzer designs, this LNA only operates from 0 to 3 gigahertz in concert with this low-pass filter. If you're looking at weak signals above 3 gigahertz, you typically will not have a built-in low-noise amplifier inside the spectrum analyzer, and you will, in fact, need to then install your own auxiliary LNA here at the input if you want to get low noise preamplification at frequencies above 3 gigahertz. Here's the catch. If you need to do that, and we'll talk about this in a later measurement talk, if you need to do that, if you need to use a low noise amplifier at frequencies above 3 gigahertz and you need to go back here to an LNA that operates, say, from 3 to 18 or whatever gigahertz, you now no longer have this filtering in front of this LNA. This LNA can be overloaded by strong signals that are not on the frequency where you're trying to make a measurement. And so you end up having to also provide your own filtering in front of this auxiliary LNA out in front. And then if you're going to do that, you'll also have to typically provide your own variable RF attenuation. So bear in mind that basically if you're trying to use a spectrum analyzer to look at weak signals above 3 gigahertz, you may need to build your own front end, and this is what we do at ITS, to operate on those signals, and your own front end will contain its own LNA, its own bandpass filtering, and its own variable RF attenuation, and you would put all that out here in front of the spectrum analyzer like so, and this would be part of a custom front end. And this is optional. Now, why would you need to have a low noise amplifier here? The reason is that spectrum analyzers typically have relatively high noise figures, and by relatively high noise figures I mean that it is not unusual to see noise figures in spectrum analyzers where we're not going through an LNA, which are on the order of anywhere from 25 to 45 dB. The reason primarily is that having passed through this RF front end system, we now pass through any one or two or three of a series of mixers like so, and these mixers bring the RF signal frequency down to an IF frequency. Oh, sorry, I was remiss on one thing. This stage, and I'll write this in green, controls sensitivity, measurement system sensitivity. Include that for the sake of completeness. Now, after we've gone through one or two or three stages of mixing, and how many stages you go through depends both on the design of the spectrum analyzer and also on how high your RF frequency is, we then will go ahead and rewrite this for greater than 3 gigahertz. We then get down to the intermediate frequency, IF, where the rest of the signal processing will be done. In many spectrum analyzer designs, at this point where we get down to the IF, we have an IF tap point available at the back of the spectrum analyzer so that we can actually attach something like an oscilloscope, for example, a digital oscilloscope, that we can use to monitor the RF signal with its phase information intact. The only difference between the signal we're measuring here and the signal that was received being that it has been mixed down through a series of stages to a frequency that is typically going to be 10.4 megahertz or possibly 21.4 megahertz. Now, at this stage, we come to an IF filter section. This section consists of a set of filters which vary in their bandwidth, and I'm going to draw them to look like this. This represents a set of 3 such filters, 1, 2, 3. In reality, various spectrum analyzer designs may have a dozen of these available. Typically, in this IF filter stage, these are designed to have Gaussian shapes. The bandwidths that are specified for the spectrum analyzer are in fact specified at the 3 dB points, at the points where the filter's shapes fall 3 dB below the nominal maximum passband of the filter. We take the bandwidth, and this becomes the so-called bandwidth of the filter. Again, usually Gaussian shapes. It turns out that in many respects the IF filter stage is the critical stage of a spectrum analyzer design. We'll talk about this in more detail shortly, but fundamentally any input spectrum that comes into the spectrum analyzer and moves through this set of RF stages and down conversion, and I will write down conversion here, frequency down conversion, frequency down conversion, will ultimately be convolved. This is a convolution stage, will be convolved through these filters such that the final spectrum that we see displayed by the spectrum analyzer will not look like the initial spectrum that came in from the outside world at the RF input, but rather will look like one of these filter shapes passed over the input spectrum shape. The way that the spectrum analyzer uses this filter is to, in fact, sweep this filter in the frequency domain at the IF stage frequency using a voltage-controlled oscillator. I'll write it here. Using a voltage-controlled oscillator. This thing will sweep in frequency back and forth across the IF stage using a VCO. And what we'll see will be the result of convolving this shape as it sweeps across the IF frequency range with a voltage-controlled oscillator convolved on top of whatever the input spectrum was. And just checking a note here. Now, the next problem that we have is, again, dynamic range. We recall that we already dealt with the dynamic range problem here in terms of getting the proper RF attenuation settings so that we don't saturate the spectrum analyzer. Here, the next step is to pass through either a log amp, a logarithmic amplifier, which we'll draw like this, or not. We'll draw the straight through like that. In fact, linear. Call this. Okay. The function of the log amp, as the name implies, is to, in fact, take the log of the power that we're measuring here, and this is the stage where we, in effect, convert power readings into decibels. If we do not pass through the log amp and we go through this linear stage, then the power levels that we'll measure will in fact be linear power. Like so. In most applications, for most purposes, we will in fact go through the log amp, like so. But there are some limited cases and some limited purposes where we want to measure linear power. Bear in mind, however, that if we're measuring in decibels, we'll typically have a dynamic range available on the spectrum analyzer display that will run anywhere from 60 to 80 dB. Whereas if we're running in a linear power range, we'll typically be stuck with about 10 dB of total dynamic range. So, dynamic range equals 10 dB versus dynamic range of 60 to 80 if we go through the log amp. Now, the next stage in the system is a detector, which is an envelope detector, which I'll draw like this, as if it were a diode. The envelope detector acts as a squaring circuit. It converts the RF waveform, which might look like this, into an envelope which will look like that. And it is at this stage that we in fact lose phase information in the waveform. I am not aware of any spectrum analyzer design that does not incorporate an envelope detector, and bear in mind that this envelope detector is not operator selectable. So any spectrum analyzer display is in fact going to show you only the envelope of the waveform, not the full complex waveform with the phase information after it passes through the envelope detector, which means that in terms of data output from the spectrum analyzer, the last stage where we can get information out that does incorporate phase information will be this IF tap point. Here, phase information is available. Downstream in the spectrum analyzer, that information will not be available. Now, following the envelope detector, we have a stage which is needed in analog spectrum analyzer designs and which can probably be primarily disposed of or dispensed with in digital designs. And this is an operator selectable set of low-pass filters, and this is the video, the so-called video filter stage. In analog spectrum analyzer designs, the point of the low-pass video filtering is to, in effect, smooth the waveform, remove high-frequency components, and functionally provide an average power measurement. Many measurement specifications for use with older spectrum analyzer designs specify that the video filter bandwidth be set to a fraction of the IF, or resolution, sometimes called resolution bandwidth. For example, we might use a 1 megahertz resolution bandwidth. That's the same as saying a 1 megahertz IF bandwidth. And that could be paired with a 1 kilohertz video low-pass filter bandwidth in order to get the average power in the waveform without having to resort to a root mean square detector. The reason that this functionality exists in analog spectrum analyzers is that analog analyzers do not provide root mean square detection as such. So we get a pseudo root mean square detection capability by going to a narrow video filter bandwidth. If in fact we're not looking for average power in a waveform, typically we will keep the video filter bandwidth equal to or greater than the bandwidth of the resolution bandwidth, or the so-called IF bandwidth stage. So if we want to measure a waveform in 1 megahertz and we want to see that waveform only convolved with the 1 megahertz filter, we would set the video bandwidth to 1 megahertz or 3 megahertz or any wider value. But if we wanted to look at this waveform in a 1 megahertz bandwidth as an average power level, then we would set this to 1 megahertz and we would set this to, say, 1 kilohertz. Now, this stage is not required in modern digital spectrum analyzer designs, because in modern spectrum analyzer designs we have a discrete component root mean square functionality. We get that by actually being able to divide by 10 and take the anti-log of these numbers out of the log amp in a digital design, and we're able to, in effect, sample the waveform and calculate the root mean square directly. But in any given spectrum analyzer design, we now pass to a stage where we pick a detection, and this detection can be positive peak. We'll talk about that in more detail in a moment. Or negative peak, or so-called normal detection, or so-called sample detection, or root mean square, RMS detection, if in fact, and I'm going to make a note of this, if in fact we're using a digital spectrum analyzer. Digital spectrum analyzer designs only. The way that this works is, in fact, to have a switch, in effect, which allows us to pick between these detection algorithms. And over here we have the same functionality built in reverse for the switch circuit. And lastly, we pass through an analog to digital converter, and then we go out to the spectrum analyzer display. We also go out to whatever data ports are available in the spectrum analyzer design. And so we'll flag this as operator selectable detection, analog to digital conversion if it's an analog spectrum analyzer, and then the final output stage, like so. So let's review the spectrum analyzer again briefly. RF signals pass into the front end of the spectrum analyzer. We control the dynamic range of the spectrum analyzer with a variable RF attenuator that ranges from 0 to 70 dB. Typical maximum power level that you're allowed to put in before you'll probably damage the spectrum analyzer at the input is 30 decibels relative to a milliwatt. That's equal to 1 watt max power. We may saturate the spectrum analyzer before we reach 30, but we won't damage it until we reach 30 typically. And by the way, this is usually written as a note on the front panel of the spectrum analyzer, and it'll be noted in the spectrum analyzer manual, this maximum power limit. Next, we isolate the signal that we're measuring on its frequency from strong signals that are not on its frequency with either a low-pass filter that works from 0 to 3 gigahertz if we're working in that frequency range, or else with the yttrium iron garnet filter that works at frequencies above 3 gigahertz, which is electronically tunable and which is controlled automatically in terms of its tune frequency inside the spectrum analyzer. Next, we control the sensitivity of the spectrum analyzer by either going through a low noise amplifier or going through a straight through path. Next, we perform frequency down conversion, which gets us from the RF frequency that we're trying to measure down to a frequency of either 21.4 or 10.4 megahertz typically. Now, one brief digression in this regard. Have you ever noticed, or if you haven't used a spectrum analyzer, you will notice that when you first turn on a spectrum analyzer, especially one of the older especially one of the older analog spectrum analyzer designs, that initially when you turn on the analyzer, you see a set of stair steps running across the analyzer like this, like so, across some frequency range that might go from, say, 30 megahertz down at the low end to, let's say, 18 gigahertz up at the high end. What you're seeing in the stair-step pattern is the increasing noise level of the spectrum analyzer internally as a function of frequency, and the reason that we're seeing this increasing noise level, which represents increasing noise figure values for the spectrum analyzer from its lowest to its highest operating frequencies, is because to mix down from RF frequencies to the IF frequency, as the RF frequencies go higher and higher and higher across here like this, we have to go through more and more mixing stages. And every time we pass through a mixing stage, we add about 5 dB of noise figure to the spectrum analyzer's internal noise. So go through one mixing stage, you pick up 5 dB of noise figure. Go through a second mixing stage, you pick up another 5 dB of noise figure, and so forth and so on. And so, this display as I've drawn it shows that to reach this frequency, we have some particular noise figure. Then, across the next frequency range, and I'll number those frequency ranges 1 and 2, to go across frequency range number 2, we have to go through an additional stage of mixing, and if we check that stair-step height, we'll find that that's about 5 dB. Then, to get to the next frequency range, which we'll label frequency range 3, we have to go through another mixer. We add about another 5 dB of noise figure there. The stair-step goes up another 5 dB, and so forth and so on. And so we can see that although the spectrum analyzer might start with a 25 dB noise figure, let's say, here in this first range of frequencies, the noise figure here is 30 dB, 35, 40, and finally 45 dB noise figure by the time we get to the highest frequencies that this hypothetical spectrum analyzer provides. This is actually a very reasonable set of noise figures for a typical older analog system design. In newer spectrum analyzer designs, where fewer stages of mixing are required to reach high frequencies, we may find that in fact we have only about one stage of mixing to get ourselves up to the highest frequencies, and so we end up with some of the newer spectrum analyzer designs having a 25 or so dB noise figure at lower frequencies, and then only about a 30 dB noise figure at the higher frequencies. And this really does represent an improvement in spectrum analyzer design that's been made in the last 10 years or so. Now, having talked in general about how the, excuse me, we'll continue and just walk through this one more time for the overview. Then we can either tap out information from the back of the spectrum analyzer, typically on a BNC connector at the back that still contains the phase information in the original waveform, simply mixed down to IF frequencies, or we can now pass through any one of a set of IF filters. These filters are controlled with a voltage-controlled oscillator voltage. They sweep across the IF frequency range. We convolve the input waveform with these filters, and we'll discuss why we have to convolve in a moment. And this is the so-called IF filter setting, or resolution bandwidth filter setting, or IF bandwidth filter setting. It's all the same thing. This is, in many respects, where the key processing occurs inside any given spectrum analyzer design, because this fundamentally affects what your measured spectrum will look like. We then convert the spectrum into decibels if we want to get a decibel display using a log amp. At this point, we're essentially taking 10 log of the power that we're measuring, although in certain limited cases we may dispense with that and go through a linear stage. The difference being that if we go through a linear path at this point, we'll get 10 dB of total dynamic range for the spectrum analyzer, as opposed to 60 to 80 dB of dynamic range if we go through the log amp. We then pass through an envelope detector, which we've drawn schematically as a diode. This is where we lose the phase information. We lose the phase information in the waveform, and we go to a spectrum power envelope. Then we pass through, especially in analog designs, although it's still available in digital designs, a low-pass video filter stage. And this filter stage allows us to get an average power measurement if we are using an analog spectrum analyzer where we do not have digital capabilities that allow us to calculate a root mean square power level directly. And then finally, and we'll talk about this more in a moment, we come to an operator selectable choice of positive peak detection, negative peak detection, so-called normal detection, sample detection, or root mean square detection if we do have a digital spectrum analyzer. And then if we have an analog design, we actually convert analog to digital. And then we come to the display section and data output ports on the spectrum analyzer. Now, you may be asking, what if we do have a so-called digital spectrum analyzer? In a digital spectrum analyzer, the RF stage components are built basically the same as they are in an analog analyzer. The differences occur in a digital analyzer relative to an analog analyzer after we've gone through our mixing stages. Once we get down to the IF frequency in a digital spectrum analyzer, we pass into, I'll draw it like this, excuse me, draw it like this actually. We pass through an application-specific integrated circuit, a so-called ASIC, and this ASIC, which is a very powerful digital processing stage, performs all of the functionality that I've just outlined inside the black box. So this is all performed by an application-specific integrated circuit, an ASIC chip, in digital spectrum analyzers, like so. Although the processing is done digitally by the ASIC chip, the functionality that the ASIC chip implements is the same as we have already seen for the analog analyzer. The main difference being that the ASIC chip capability in the digital analyzer, as I've said, allows us to actually compute root mean square power averages, which are not otherwise available in an analog analyzer, where, as I said, we have to use the somewhat less than ideal expedient of using a narrow video filter setting, narrow compared to the IF filter setting. Now, at this point, I want to talk briefly about what the different types of detection actually do for us when we're looking at different waveforms. And then we'll come back and talk briefly about the convolution functionality in the spectrum analyzer, because this is, as I said, in many cases, the key aspect of what a spectrum analyzer does when we use it to look at spectrum. We'll split the board up this way. This half of the board will be devoted to a brief description of detection as implemented in spectrum analyzers. This side of the board will be devoted to a discussion of convolution as understood in the context of measuring waveforms with spectrum analyzers. Again, the detection techniques that we have are positive peak, negative peak, so-called normal, so-called sample, and root mean square. To show what the differences are, I'll actually draw a spectrum analyzer screen like so. Typical spectrum analyzer screen is displaying frequency and displaying power. Remember, envelope power as a function of frequency, and is in fact broken up into discrete display bins. Now, a typical number of display bins is 1001 in some classic spectrum analyzer designs. This is sometimes an operator selectable parameter and sometimes locked into hardware, but the point is that any time that we're displaying power on a spectrum analyzer, we're going to display the power in a series of these bins, and these will be the power levels. This is the power level for bin number 1. This is the power level for bin number 2. Here's the power level for bin number 3, and so forth across until we finally get to the displayed power level in bin number 1001, the way that I'm drawing here, at the far right-hand side of the screen, like so. To the eye, these look like they're fairly well connected, and we'll see something that will look like this. But bear in mind that these are typically discrete points that are in fact being displayed as a set of bins, and that the spectrum analyzer's frequency sweeping here is synchronized with the sweeping of that voltage-controlled oscillator that we see down at the IF stage. Now, here's the problem. In any given bin, and let's look initially at bin number 1, like so, we see that if the spectrum analyzer sweeps in some time that we'll call T sub sweep, which, for example, and we'll make it easy here, we'll make it 1001 milliseconds. So it takes 1001 milliseconds to sweep across this range. That means 1.001 seconds of actual time to sweep across this range. That means that if we're doing 1001 bins in 1001 milliseconds, that in fact this spectrum analyzer is taking a total of 1 millisecond of scan time or sweep time for every bin that it's displaying. But the waveform that we're trying to measure, which might well look like this in the time domain, this would be characteristic maybe of some type of noise, for example, will in fact vary within that interval. So here we have an interval of 1 millisecond. The problem is that the waveform is varying inside that interval of 1 millisecond. And so the question is, what will the spectrum analyzer display as the single power level that it can show for that first bin in that first millisecond during the sweep time? This is where the detection comes in. If we have picked positive peak detection, then this is the value that is going to be displayed. The highest value that occurs during the bin sampling interval is what the positive peak detector is going to show us. So if we're looking at positive peak detection, we'd see a value maybe all the way up here on this waveform. So much for positive peak. Now, suppose we're looking at negative peak. As the name implies, negative peak is a latching function which latches to the lowest value that occurred during the sweep interval for the bin that's being displayed. And in this particular example, the way I've drawn it, this would be the negative peak value that would be displayed. And so if we were using so-called negative peak detection on this spectrum analyzer, we might see a value displayed all the way down here. So there's plus peak, there's negative peak. Negative peak displayed like so. Yes. Now, next, so-called normal detection. Normal detection is a switching operation between positive peak and negative peak on successive bins. In normal detection, bin number 1 will be picked as, let's say, positive peak. The next bin, which will occur in the next millisecond, will extend this time waveform like so, will therefore be picked off as negative peak down here. And in the next bin, we pick off positive peak and so forth all the way across on the spectrum analyzer. The result being that if we're running in so-called normal detection, we will actually see a display that looks like this, and it'll look like it's tracing out an envelope like that. And in reality, we're going plus peak, then negative peak, then plus peak, then negative peak on alternate bins all the way across the spectrum analyzer. The spacing between the bins being so closely packed that we seem to see a big band of color running across. Most spectrum analyzers, when they first turn on, will in fact be running in so-called normal detection, and that's why we see this big band running across the spectrum analyzer display when we first turn it on. Now, sample detection. Sample detection is nothing more than the collection of the last measured power level in a bin, period. Whatever that power level is, that's what the sample detector gives us. So the way that I've drawn this, bin number 1, sample detection, would return that value. Bin number 2, sample detection, would return that value. Bin number 3, if it extended, let's say, all the way over to here, and this were the end of bin number 3, sample detection would give us this value. And so, as long as the waveform that we're measuring is not in some sense correlated with the rate that the spectrum analyzer is sweeping frequencies across these bins, sample detection in effect gives us a random sampling inside the waveform because we're simply picking off the nth power value available in each of the bins, the nth being the last power value that each bin saw. And finally we come to root mean square. In root mean square, a running average is actually kept on measured power levels on the waveform as the waveform evolves inside each bin. And you can see that this is not practical to implement in analog designs, but it is practical to implement in digital designs where we have a sampling capability built into the spectrum analyzer. And inside each of these bins, we may get thousands or even millions of these samples, numbered 1, 2, 3, 4, etc., all the way up to n. And then we take the actual linear power average, not the decibel power average, but the linear power average of all of these values in this bin, and that will be displayed as the true root mean square power value, which for this bin, the way that I've drawn it, might be a level that might look something like that. And so root mean square would presumably be a power value like that for the first bin on this spectrum analyzer display. Now, there are a couple of other averaging techniques available on analog and digital spectrum analyzers. One of them is a so-called decibel average. And in a decibel average, the decibel power value that's been measured on each of these bins is in fact averaged from one sweep to the next. So we'll take this bin right here. We'll get a decibel power value for it on sweep number 1. Then the spectrum analyzer will sweep again, get a decibel power. It'll add the 2 dBs together and divide by 2. On a third sweep, it might get a power value here. Then it adds all 3 together, divides by 3, and so forth. And this actually takes an average of decibels, not a linear power average, if the spectrum analyzer is being run in this mode. This is a screen trace display mode. Just be aware that if you use it, you are getting average decibels, not linear power average, and there is a difference. How much of a difference you get between the two depends upon the type of waveform that you're trying to measure. And lastly, there is typically a screen averaging or a trace averaging capability that may be slightly different from the decibel averaging in some spectrum analyzer designs. In any event, the only way to get true root mean square power is in fact to have a digital spectrum analyzer with RMS detection built in, or come close to RMS using the video filtering. One thing that I do want to point out with that said is that if you're using an analog spectrum analyzer and you want to get average power using narrow video filter widths compared to the IF filter widths, that in fact, because we're working with these video filters after the log amp stage has been passed, we'll get a decibel, and I should make note of that we will in this case get a decibel power average, not a linear power average, if in fact we use this technique with an analog spectrum analyzer. Now, last thing that I want to cover in this talk today is convolution. We've already talked about the IF filter stages. And what we have schematically is an input function to the spectrum analyzer, G of omega, that looks like this, we'll say, where this is frequency versus power, like so. And we are going to move an IF filter across this, and we'll call this F of omega, label it in green. We're actually going to move this filter shape across this spectrum, and the result is going to be a function h of omega, which is equal to the convolution of f of omega convolved, convolution symbol, convolved with g of omega, like so. And this convolution shape will look something like this, the way that I've drawn it here. Now, why do we have to do this? The reason fundamentally is that we have to use some filter shape here that has some finite width to it. If this filter shape were to go to 0 width, like so, then f of omega convolved with g of omega would in fact look like the input function, but the amount of power that we would be able to get through this would be in effect 0 power, and we would not be able to measure any power through the filter. Secondly, in order to get across any non-zero amount of spectrum on, for example, this display where we're moving a filter across, if we had a 0 width IF filter being moved across, like so, then it would take us an infinite amount of time to step this filter across in such a way that we would get successively overlapping steps like this that would allow us to sample the spectrum without gaps. And I'm going to explicate a little bit graphically how this works. suppose that our input waveform, in fact, looks like a sine wave in the time domain, like so. Here's time, sine wave. In the frequency domain, the waveform will look like this. The emission is on a single frequency. And now we're going to move an IF filter, represented like this, across it. As we move the IF filter across, we'll look at the output on the spectrum analyzer. Down here, here's the spectrum analyzer output. So at this point, we're just measuring noise in the spectrum analyzer. Now we step the filter across like this. We'll measure noise again. Now we step the filter across like this. Now, at this point, although we're tuned to this frequency, we're getting this much power from this sine wave, and so now we see a power level displayed up here. So up to this point we were measuring noise. Now we begin to get power, step across like this. Now we get the full power in the waveform displayed on this frequency right here, like so. Continue stepping our way across at this frequency, somewhat less power again, like so. And then finally, we're back to measuring spectrum analyzer noise down in here. And we see that what happens when we move this IF filter across this sine wave is that we don't see the sine wave in the frequency domain, which looks like an impulse in the frequency domain, but rather we get a picture that looks like this. And in fact, although I've drawn it a bit crudely, the actual result that we'll get will in fact look like that on the spectrum analyzer. Now, at this point you can say, let's use a more narrow filter so we can get a better fidelity between what we're measuring and what the waveform actually looks like. We sweep a narrower IF filter across like this, and now what we're going to get is a picture that's going to in fact look like this. There we are. A little better. But we had to take more steps to move this narrower filter across, so we have to sweep the filter more slowly. And most spectrum analyzer will automatically slow down in order to do that. Now we come to an even narrower filter, we move it across. It takes longer to move it across, we have to take more steps with it, but we get a little better fidelity picture, like so. And so now with the more narrow filter, the measurement takes longer to run, but we get a better picture of our signal in terms of seeing the width of the signal. Now, can we ever make a measurement that'll show this signal for what it is, being 0 hertz wide? We'll assume it's a pure sine wave. And the answer is no, because to do so we would have to use a 0 width slit, which would allow 0 power through and would take an infinitely long amount of time to step across the spectrum. Well, these are the fundamentals for the spectrum analyzer as seen on a whiteboard. Now we'll transition to the lab portion where we'll actually look at some signals like this with a spectrum analyzer, and we'll look at the various functionalities that I've just described. Okay, welcome to the lab portion of talk number 2. In this section, what we're going to do is take a look at a carrier wave signal with a spectrum analyzer. This is not a particularly complex signal type, but it allows us to see how we can exercise various aspects of a spectrum analyzer with a simple signal. So to begin with, we've turned on a spectrum analyzer. We notice that we have the attenuation level at the front end set at 10 dB, and what we want to do is get that down to 0 dB for this talk. So we go over here, attenuation manual, and we'll go ahead and step the attenuation down to 0 dB, like so. Now, the next thing that we want to do is look at what center frequency we want. We're going to bring up a signal at 2 gigahertz. So we'll go frequency, center, 2 gigahertz. And let's take a look at a span of about 20 megahertz initially, like so. And for this particular signal, by the way, the center didn't come up at 2. All right, it switched back, so we'll go back to center 2. There we go. Center 2 gigahertz, span 20 megahertz. So now, in terms of the frequencies that we're looking at, we're going from a start frequency of 1.99 to a stop frequency of 2.01 gigahertz. Let's start by looking at the signal in fact, a 3 megahertz bandwidth, and we'll slow the sweep time down just a little bit, although that's, for this particular purpose, not a terribly important feature to worry about this moment. Now, next thing that we'll take a look at is detection. You'll notice that we are seeing this wide 30 dB, a little more, almost 40 dB range of power values. So we'll go ahead and look at detection, and we see that in fact we are locked at the moment into so-called normal detection. That means that on alternate bins, and we have 601 bins across on this display right now, down here in the lower right-hand corner, we see the indicator of that. We're going from positive peak to negative peak to positive peak to negative peak to positive peak to negative peak as we go from one bin to the next. So we're getting 300 positive peak bins across, we're getting 301 negative peak bins across. What we can do here is, in fact, go to either peak detection, in which case we're seeing a trace that looks like the maximum level, and we saw this in the last talk, or we can go to negative peak, in which case we're getting levels down here, and again we saw that in the last talk that we did. But we can go sample, in which case we're pulling a random point off on every spectrum analyzer bin. The random point comes off at the end of the sampling interval for the analog to digital converter for each one of these bins every few microseconds. And what we're seeing here, of course, is the noise characteristic that we saw in the last talk. But to look at the carrier wave, although it's not terribly important to pick this particular detection, let's go to average detection. So we pick this selection right here, average. And now we will go ahead and turn on a carrier wave signal. So here's a carrier wave signal. Now, in the time domain, this signal looks like a sine wave. In the frequency domain, what we see here is a bump, and this bump, if we measure its width at the 3 dB point, where the amplitude on this curve is 3 dB below the maximum level here, we'll see that in fact that bandwidth is 3 megahertz right there. In fact, I'll go ahead and demonstrate that. We'll go to peak search, and then we'll go marker delta. We'll come down 3 dB below that peak level, so we're right there, and then we'll go delta again, so now we get the delta from here to the other side. We'll go to the same level on the right as we are on the left, and what we see is that we see this bump 3 megahertz wide. Now, people sometimes see this and say, oh, we have a signal that's 3 megahertz wide. We, of course, do not have a signal 3 megahertz wide. We have a carrier wave signal, which, as we discussed in the whiteboard section just before this lab, in the frequency domain, in fact, would look like a line drawn right here, but we're convolving that line emission in the frequency domain with an IF filter, which is 3 megahertz wide, which is being swept across the frequency range like this, sweep across like this, and remember that I drew the effect of that convolution on the whiteboard. We're seeing that convolution here. We see this as, in fact, a feature that looks like it is 3 megahertz wide, and this 3 megahertz width is nothing more than an artifact of the filter that we've chosen in the spectrum analyzer to use to look at the signal. So, with that said, I'm going to go ahead and freeze that trace by hitting View. Then I'm going to go to Trace 2, do a clear right on Trace 2, and now I'm going to reduce the bandwidth down to 1 megahertz, like so. We'll turn off the marker too while we're at it. There we go. Turn off the marker, and so now we see the signal convolved with a 1 megahertz filter bandwidth. And the interesting thing here is that we are, in fact, again, seeing nothing more than an artifact of the spectrum analyzer's own internal IF convolution bandwidth. Notice, however, that we are getting a little more dynamic range right here on the signal. The peak level on the signal, the maximum level on the signal, is the same as it was before. We're seeing the signal a little closer to its true characteristic of only being a megahertz wide, but we've picked up about 3 dB of signal-to-noise ratio here because the KTB noise that we discussed in talk number 1 of this series has in fact dropped by 10 log of the bandwidth. Now I'm going to go ahead and freeze trace number 2. Now I'll go to trace number 3, and we will drop the bandwidth again, this time down to 300 kilohertz. And we see now that in 300 kilohertz, we're getting the true characteristic, truer, not the true, the truer, the better characteristic of the signal in terms of its actual emission bandwidth. We're still seeing nothing more than a convolution of our own IF bandwidth, but we see that in fact whatever the signal is that we're looking at, it's narrower than 300 kilohertz. And we've now picked up 10 dB of dynamic range compared to the level where we started with a 3 megahertz bandwidth, and this is nothing more than the fact that KTB in 300 kilohertz is 10 dB lower than KTB in 3 megahertz. Now we'll continue our way down. We'll go back to trace. We'll go back to trace 1, and that's the yellow trace. We'll go clear right on it. The reason I'm doing this is we only have 3 traces available on the spectrum analyzer. And now we will, one other thing I need to do, trace 3 view. All right, back to trace 1. Now we're going to drop the bandwidth down from 300 kilohertz to 100 kilohertz, like so. Wow. Once again, we are seeing a narrower convolution characteristic, and again the KTB noise has dropped, and in fact things are getting so narrow right in here that I'm going to go ahead and actually zoom in on this part of the display so that we can better see what's going on. So we'll go from a 20 megahertz span down to half that, a 10 megahertz span, like so. We'll go trace 1 blank, trace 2 blank. Okay, there we are. Trace 3, clear right. All right, so now we're able to see a little more clearly what's going on down at this narrow bandwidth. Actually, I'm going to bring the span down even further. Let's bring the span down to 1 megahertz. There's a 1 megahertz span. We're seeing that the signal now is 100 kilohertz wide. We can even verify that by going peak search, and again we'll just check this with a delta marker. We'll roll down 3 dB on this side, delta from there, from the left over to the right, and sure enough, 100 kilohertz wide at the 3 dB point. This is a typical way of characterizing spectrum analyzer IF bandwidths, by the way, is the widths at the 3 dB point. So again, just to continue our way down, we'll go to freeze that trace. We'll go to trace 1, clear right, bandwidth, reduce it down to 30 kilohertz. We see the same pattern developing. We'll say trace view. Now we'll go to trace 2, clear right, bring the bandwidth down even further. Now, at this point, we're down to a 10 kilohertz resolution bandwidth, and we just had a MES uncal indication come up. This is an indication that the spectrum analyzer is moving this filter across the IF at a rate that is faster than about 2.5 times 1 over the bandwidth. Technically, we can't move any faster than 1 over the bandwidth, and these warning indications usually are conservative, so it'll be more like 2.5 times 1 over the bandwidth where we get the warning indication. This means that in order to get an accurate power measurement where we're not sweeping the filter faster across this frequency range than we should be, we need to in fact slow down the sweep time. So now we'll go to sweep, and we will go from 20 milliseconds to, let's say, 100 milliseconds. We see that the MES uncal indication has gone away. So we see that the price that we pay for moving across the spectrum in a finer and finer resolution bandwidth is that we have to move more and more slowly across the spectrum in order to, in fact, get accurate power measurements. In other words, there's no free lunch. We pay for better resolution by having to work more and more slowly across the spectrum. But with that said, let's go ahead and bring the span down to, we'll bring it down to 200 kilohertz. Now we're seeing the effect of a very fine frequency offset on this signal from the nominal 2 kilohertz that we thought we had it tuned to. So we'll just go peak search, and then we'll say marker to center frequency, like so. And then we will, on the trace indications, we'll go ahead and turn off these two old trace indications. We don't need them anyway. So now, here we are. We're looking at this carrier wave signal in a 10 kilohertz bandwidth. We verified that this is, in fact, 10 kilohertz across here, or at least we can verify it. And now, I'm going to go ahead and bring the bandwidth down even somewhat to a narrower value. We'll come down to 1 kilohertz, so 1 kilohertz bandwidth. And again, if we check this at the 3 dB points, we'll find that, in fact, this thing is 1 kilohertz wide at the 3 dB points. Again, we need to slow down the sweep time, and we'll do that. All right, now we're having to move at the rate of 200 kilohertz of span once every second. So we're having to move very, very, very slowly in order to not sweep that IF filter faster than about 2.5 times 1 over the filter bandwidth, which in this case is 1 kilohertz. But we are getting to see the spectrum with this kind of resolution. Now, something else I'd like to mention at this point is that we can increase the amplitude of the signal, and we'll actually get it up high enough to overload the IF. And the newer spectrum analyzers, like the one that we're using for this lab, do have an IF overload indicator. Here, what we're doing is actually overloading the IF by having brought the signal up to a power level, which on my signal generator is 0 dBm, that's 1 full milliwatt. We are producing this overload characteristic, and in order to get out of this overload characteristic, what we'll have to do is, in fact, go to the reference level on the spectrum analyzer, bring the reference level to a higher value. But we see that where we went from -20 to -10, the spectrum analyzer won't let us go any higher at this moment than -10, and we're still overloading the IF. What do we do? What we have to do at this point is, in fact, implement some RF attenuation at the front end of the spectrum analyzer. You'll remember that from the block diagram that we drew on the whiteboard earlier. And when we implement that RF attenuation, we will in effect desensitize the spectrum analyzer by 10 dB down here at the noise floor, but we'll give ourselves 10 dB of additional dynamic range up here and get ourselves out of this overload condition. So we'll do exactly that. We'll go to attenuation, 10 dB. All right, now the analyzer will allow us to go to a reference level of 0 dBm, so we're now able to get an accurate power measurement here. We're no longer overloading the spectrum analyzer. The only penalty that we've paid is that we have lost 10 dB of sensitivity down here. So if we had another signal down here at this level, at about that level that we were trying to measure, we would not be able to see it. So again, you have to consider the trade-offs when you're running a spectrum analyzer and you're looking at signals in terms of the sensitivity of the spectrum analyzer and the amount of dynamic range that you have and the overload power point that the spectrum analyzer has. Usually we're able to effectively accommodate these factors, but we are limited here to a total dynamic range of about 10, 20, 30, 40, 50, 60, 70, about 85 dB on this particular spectrum analyzer display, measuring from here 10, 20, 30, 40, 50, 60, 70, 85. Yeah, about 85 dB of dynamic range. That's all we're going to get. If we want to see more, signal up here at the max, we have to take and add more attenuation. If we want better sensitivity out on the sides at other frequencies, we'll have to remove attenuation. But if we do, we have to somehow filter down or filter out the power on this carrier wave so that we don't overload the spectrum analyzer IF. Now, at this point, we'll drop the carrier level down in power, and then we'll go back on attenuation, we'll set the attenuation back to 0 dB, and then we'll bring the reference level on the spectrum analyzer down to -20. So now we've centered up this signal in terms of dynamic range again, the signal itself having been dropped 20 dB on the signal generator. At this point, I'm going to have to step out and I'll be gone for about an hour. So I'm thinking let's just stop the tape, and then I've only got maybe another 5 or 10 minutes to go. But we can just keep all this running.
It's running.
It's running, all right.
Anytime you want, give it a smoke.
All right, so this is where we picked up after the break that we took, and I'll give it a short pause, Bill, on your edit, and then I'm going to just pick it up and run with it. Okay, so having looked at the problem of convolution, there's one other thing that I'd like to mention before we wrap up this lab, and that is what I call the picket fence problem, or the picket fence effect. Given that the spectrum analyzer is using a certain IF resolution bandwidth to look at the spectrum, we need to keep in mind when we're using a spectrum analyzer that we have a certain finite number of points, in this case 601 points, that we're graphing across a certain span, and we need to do the math to make sure that we're actually getting a convolution on the spectrum without gaps in the spectrum as we're moving what can be, in some cases, a relatively narrow IF filter across what can be a relatively wide frequency span. Let's just do an example right here, right now. We're spanning a range of 200 kilohertz with a 1 kilohertz IF bandwidth, and we're taking 600 points across. That means that we're taking 600 1 kilohertz steps across a span of 200 kilohertz, and that means that we are in fact getting about 3 points on this screen within the range of our IF bandwidth. That's good. It means that as we're spanning across this screen, we're not developing any gaps on the measured spectrum between measurement points. But let me take you to a point where we exactly balance out or exactly equal the amount of spectrum that we're convolving with our IF filter with the number of points. Let's suppose that we span a range not of 200 kilohertz, but of 600 kilohertz. So we're just going to change the span here to 600. In fact, I'll make it 601 kilohertz just for good measure. So go span 601 kilohertz. Now, it says mes un cal. That's because, again, we have to slow down the sweep rate in order to not move the filter faster than about 2.5 times 1 over the bandwidth. There. So, at this point, we're spanning 600 kilohertz with 600 points with a filter bandwidth which is itself 1 kilohertz wide. That's good. That means we're getting an exact correspondence between the data points that we're sampling and the amount of spectrum that we're sampling across. Now, suppose that we go somewhat wider. Let's go, instead of 601 kilohertz, let's double the span. Let's go to 1202 kilohertz. So I'm going to go to span 1202 kilohertz, 1202 kilohertz. Again, we get the mes un cal indication, so again, we'll slow the sweep time down. Okay. Now, it's taking us 7.5 seconds to move across here, but there's an ancillary problem that we've developed. The ancillary problem is that for every measurement point that we're displaying on the screen, we're only looking at about half that much spectrum through our convolution bandwidth. We're actually missing about half of the spectrum that's displayed on the screen in terms of convolving it with the IF filter. That means that if we had a very narrowband spectrum feature at this point, somewhere along this span, we might actually miss it. In fact, we get the effect a little bit in terms of the power that we're measuring on the signal. Note here that the power that we're measuring on the signal at this point is showing at about minus 28 or so dBm. Let's go back to where we were measuring in 601 kilohertz and 601 steps and 601 kilohertz, 601 steps, and compare that. So we'll go span, go back to 601 kilohertz. Watch what happens to the power measurement. We'll leave the sweep time kind of slow. Okay, the power measurement actually came up a little bit. That's because when we ended up measuring in a span that exceeds the number of convolution points that we can take with a filter across here, we can actually miss chunks of the spectrum. We do miss chunks of the spectrum, and we can actually fail to get the total correct power. I'm going to actually show this by actually going from 601 kilohertz to a span 4 times wider. That'll be 2404 kilohertz. So go span 2404 kilohertz. Now let's watch and see what happens. Again, we'll have to slow the sweep time down. There we go, 10-second sweep time. Now what's happening is we're actually missing 3/4 of the spectrum in this span in our measurement filter bandwidth, because we're still taking 601 kilohertz measurements across here, but we're spanning 4 times that much spectrum, and look what happened. Now the measured power has dropped down to minus 30 dBm. What's happening is none of our data points that we're using for this measurement are in fact landing right on the frequency of this carrier. And as I said, this is the so-called picket fence effect. It's something that we would normally strive to avoid when we're doing spectrum measurements. It is sort of the last piece of the puzzle in terms of getting a good convolution measurement on a spectrum analyzer, and that is just bear in mind that you want to make sure that you're not spanning too much spectrum in comparison to the width of your IF filter and the number of points that you're sampling. One very, very last thing that we can do with a spectrum analyzer like this is we can keep on sampling the same amount of spectrum, but we can, with this analyzer, boost the number of points that we're measuring with. Instead of 601 points, let's go to 2,404 points. And so we will go to excuse me, I couldn't remember for a moment which menu to go to for a number of points. There's 601 points. We'll go to 2,404 points, and before I hit the enter button, watch here when I hit the enter button, like that, okay? Now watch that location, and we should get a full power measurement now, and we do. We're back up to about minus 25 dBm. So we can either, if we have the picket fence problem, either go to a more narrow span, a narrower span, while keeping the number of data points constant, or if a spectrum analyzer allows us to increase the number of points, we can increase the number of points and maintain a wide span. Either way, you just want to make sure that you do the math either with a calculator or in your head so that you don't end up accidentally missing a lot of spectrum as you perform the convolution measurement. And that completes the lab portion of talk number 2.